A review of what you're supposed to know. Beginning here, concepts as review, and also to introduce you to the notation that we are using in this class. Okay, so you may have called it something else in your prerequisite course, okay, or used a little different notation. So to begin with, H0 denotes the null hypothesis, or the hypothesis of no difference or change. The alternative hypothesis in this book is given by H1. Some textbooks use an HA for alternative. That's our research hypothesis, or poses our research question. The test statistic, a measured outcome of the experiment designed to test the research question. So we've talked about t-tests, z-tests, chi-square tests, those kinds of things. Those values are called test statistics. Rejection region, a criteria the test statistic must meet in order for us to support the alternative hypothesis. And a written conclusion on our hypothesis test. So it's really kind of these 5 things. And most typically what we do instead of a rejection region, because we're working with computer software, is that we look at a p-value, or an observed significance level is really the formal term by which it's called. And so those are terms that sound familiar to you. The p-value is the probability of obtaining the observed test statistic, or one more extreme. And we'll look at examples of that as we go through our problems. Possible decisions or conclusions that we come to generically are the reject the null hypothesis or fail to reject the null hypothesis. We will always write conclusions in the language of the problem, and so the term that those 2 expressions will never be correct as a conclusion. I want it in the context of the problem. So if we decide to reject the null hypothesis based on sample information, we may be making a mistake, and so we may have done a similar kind of a chart in the prerequisite course. If the null hypothesis is true and you reject the null hypothesis, you've made a mistake, and this was classified as a type 1 error. And we can control this probability of a type 1 error and we set it equal to a value Greek letter alpha. If the null hypothesis is true and we fail to reject it, then we have made a correct decision. If the null hypothesis is false and we reject the null hypothesis, that is also a correct decision. And if the null hypothesis is false and we fail to detect it, that is, we fail to reject the null hypothesis, we've also made a mistake, and that was referred to as a type 2 error. The probability of a type 2 error is equal to the Greek letter beta. Now, if the null hypothesis is false, okay, and we detect it here, so that, remember, these 2 events would be complementary events, meaning that their probabilities sum to 1. And so that if the null hypothesis is false and we detect it, then this would have probability 1 minus beta, right? And so that's referred to as power, or statistical power. And so we like our tests to have good power. If the null hypothesis is false, we want our probability to be high that we're detecting it. Now, the one we actually have control over is alpha. Okay, we set alpha in all those tests. So you remember talking about alpha equals 0.05 and 95% confidence intervals and things in the previous course. Alpha and beta are related to each other as our probability of a type 1 error increases, value of beta decreases. As alpha increases, then we are making this error more frequently. So if we're rejecting more often, then we're not going to make this mistake as often, right? And the only way we can really control beta is, well, that's kind of a function of, well, how false is the null hypothesis, and that's what we don't know. If you continue with me in experimental design, we do more talking about power and how to calculate power and improve power. What we started with in the previous course was some measurements from a single population. So we drew a sample of size n from a population. We measured sample mean and sample variance from that group of size n. Distributional property of y bar. You might remember that we spoke about something called the central limit theorem. All right, and so just given here the two-sided test for the population mean equal to some specified value mu 0, aside from the null hypothesis with its subscript 0. Whenever we see a subscript 0 here, that usually means it's an assigned value. Okay, so we're comparing the mean equal to some named or assigned value, and that was done by a t-test. And if that t had an absolute value that was large, we had a decision rule in there that we would reject the null hypothesis if our computed t had an absolute value that was large, and it was larger than that determined by t, determined by right-hand area alpha over 2, and the degrees of freedom for the application. And similarly, we would compute a confidence interval for mu. We'd take our sample mean plus or minus this critical t determined by the degrees of freedom times the standard error of the mean, the standard error being the denominator. The degrees of freedom for this application is n minus 1. Population is not normal. There are non-parametric methods that can be used for the test of hypotheses. You may or may not have examined those in the previous course. It's one of the things that may have looked a little different, whether you did any non-parametric examples or topics. We increased the number of populations to 2 in the previous course. And so what changes then, we have 2 populations. We measure a sample mean y bar with subscript 1, a sample mean y bar with subscript 2. So the subscript indicates from which population these come. Likewise, the sample variances and sample sizes are indexed in this way. And we were interested in comparing 2 population means for equality. There were 2 different approaches we had for this. One was that if our sample sizes were independent of each other, there was nothing linking the observation in sample 1 with the observation in sample 2. And so we computed a pool variance estimate. Sorry, my formula kind of crashed into our text up there, didn't it? That was our pooled variance estimate of sigma squared. We had 2 approaches. So if our populations had equal variances, some value of sigma squared that's unsubscripted, and we had these samples that were independent, we pooled our information together to come up with one better variance estimate. And we computed a test statistic for it as well, and the degrees of freedom. So previously I said the degrees of freedom for this application. Here is a second application of a t-test, but the degrees of freedom depends on the application. Okay? So it was the combined sample size minus 2 for that application, and likewise then we can also compute confidence interval for the difference between the 2. If the variances were unequal, sigma 1 squared equals sigma 2 squared, we did not compute a pooled variance because it would be an estimate of nothing these 2 populations have in common. And then you would look at a t-statistic and had this expression here for degrees of freedom, and this that I call df star, and this is the Satterthwaite approximation. Satterthwaite degrees of freedom approximation. So when I cover this in the previous course, it's not one we do by hand. We let the computer software do it. So we have these 2 issues here. The variances are equal to each other, or that they're not equal to each other. And so just, how do we know? Why do we care? Right? How do we know if the population variances are equal, and why does it matter? Well, how do we know? There's a test then that for comparing the 2 population variances that was done with an F statistic. And so that we look at this value of f, and so it's taking the variance from one sample divided by the variance of the second sample. And then remember, F statistics have both numerator degrees of freedom and denominator degrees of freedom, always. For this application, those degrees of freedom are given by the numerator sample size minus 1 and the denominator sample size minus 1. And so that if the null hypothesis here were false, okay, and so if the null hypothesis is false, and let's say sigma 1 squared is much larger than sigma 2 squared, if sigma 1 squared is larger, S1 squared is going to tend to be larger than S2 squared, and the value of F is going to be very large. If it were the case that sigma 1 squared were much smaller than sigma 2 squared, this value of F would be close to 0. F takes values between from 0 and increasing. So we look at the tails of that distribution. Why do we care? Suppose I have a population. My first population. Okay, and I've drawn it as a normal population. Mean of mu1. Remember, the area under the curve is equal to 1, right? Whenever we look at probability distributions. If I have a second population, suppose it has the same mean, but it's very narrow. Got up into our text here. If it were, so I say our population 2. Okay, and mu2 is exactly the same as mu1. So if I have two variances that are very different from each other, I come back to these and I measure a y. I draw a sample of size n1 from population 1, and I measure a value of y1 bar. And then that's a likely value. It's not real far into the tails of the distribution. And I suppose then I could also measure a likely value for y2 bar. Okay. As we look at this, if we were to compare the two variances here, our sigma 1 squared, this is a much broader distribution, is much larger than our sigma 2 squared. Okay, and so if I don't handle this correctly, if I pool those two variances together, that would be a poor idea because they're quite different from each other. But the other part of it is I might judge, if I don't handle this carefully, I could judge these two differences, the difference between these two sample means to be profound, and say that they are different population means when in fact they are not. And so what I'm really picking up is a difference of the variances. So we want to make sure we use the right method, either the equal variance method or the unequal variance method, so that we can say what we're detecting is attributable to differences in population mean and not differences in population variance, right? If we have two populations that we're sampling and our samples are dependent, that is, we got our two samples and they're somehow related to before and after. Sometimes in genetics they look at identical twins, and so they look at one twin of each pair. Those are linked. There's something linking those two things together. Those samples are dependent. And so I need a different method of analysis when the samples are dependent than I need when they are independent. And so recall that you computed the difference across the pair, and then computed what the average difference was given by d bar here. And then we look at the standard error for the differences. The standard deviation of those differences divided by the square root of sample size. Okay, so it just retakes if they're dependent, we took that difference and kind of just reduced it down to a single population t-test, if you will, because it still ended up then with the common sample size minus 1 degrees of freedom, or how many differences were there. If the populations are not normally distributed, again, there are non-parametric methods that can apply. What this concept of dependence we'll look at later in this course where I have not just 2 samples that are dependent, but more than 2 samples, and that concept is referred to as blocking. So some of you have heard of blocked experiments, and so that's when you have 2 or more dependent samples. So how I summarize things are as follows. I could have written one-sided tests in here as well, but what are our hypotheses? The test statistic, the very first page we talked about, right? What do we measure from the data? Well, we measure our sample information, the Y1 bar and the Y2 bar, this pooled variance estimate, and we compute a test statistic. If this test statistic is extreme, then that would support the alternative hypothesis. So extreme is one that is into the bar tails of the distribution, either to the right or the left. That's why we're taking the absolute value. The conditions or assumptions we're operating under are these. Okay, so that's just summarizing everything we did before. So now then our what if, well, what if this variance was not, these variances were not equal to each other? This test statistic computed, there's no S sub p value in here, right? Because we're not pooling things together. We still look for an extreme test statistic, and we have a degrees of freedom approximation method here, right? So in order just to shorten things up, I use this tabular arrangement frequently. When we're comparing variances, we use an F-test. And we said that we would reject for values of F that were very large or very close to 0. So this would represent F values that are very close to 0. What the F distribution looks like. So we're looking at values here and far to the right. If the null hypothesis is true, the value of F we would expect to be very close to 1, wouldn't we? And then our dependent samples, so that's what changed over here. Our hypothesis doesn't look any different. It's our condition over here where we had dependent samples that changed. And the differences are normally distributed, and that's why we're using a t statistic. In each case, the test statistics are compared to critical values from the appropriate reference tables. For the application, you need to know the degrees of freedom you're looking up. We determine if it's extreme. So if it's an extreme test statistic indicates that the null hypothesis may be false. Additionally, we can compute an observed significance level or p-value. You should have done this in the previous course. So general rule for everything we do, for all of our applications. If our p-value is less than or equal to the set value we allowed ourselves for a type 1 error, we reject the null hypothesis. Or if you say, look up the rejection region and you determine that you should reject the null hypothesis, you better report a p-value that's small. Those pieces logically have to fit together. Likewise, if we see a p-value in excess of our type 1 error rate alpha, we would not reject the null hypothesis. Or if by using the rejection region we determine that we do not reject the null hypothesis, the p-value we report better be larger than alpha. Okay? On the course essentials module, if you scroll down past some of the documents, the miscellaneous review items, there are short videos that I took from my 5013 class on how to find p-values for a t statistic and an f statistic. Okay? So if you need to review that, please do